Hello, can everyone hear me? Good, good. Right, how you all doing? Good, good to know. Right, I'm Luke. I'm here to talk to you about optimization in business. So this is a part of data science which I would say it's often, I wouldn't say forgotten about, but often neglected. So this is about optimization. So normally with data science, you always hear of regression, classification, clustering, those sort of methods. Those come under descriptive methods. But then quite often there's another part of the puzzle, which is once you know what's going to happen, what do you do with that? What actions do you take? And that's in the realm of prescribed methods. And that's sort of what optimization comes under. And I've come across it quite a lot, and quite a lot of businesses don't think to do it. So the aim of this talk is to give some food for thought for ways you can apply it, because quite often it's not always obvious. And so this is just the outline, of course. So just a little about me, what and why about optimization, and then I'm going to run through some examples in these avenues to explore if you were interested, then run through a little bit about the issues with optimization, and I'm going to try and keep the technical stuff to a minimum, but I'll speak about some technical stuff at the end. So, yeah, a little bit about me. I had a bit of a weird route into data science. I didn't start off down that trajectory. I was involved with research to do with nuclear fusion, which was very computationally based on materials modeling. And then I jumped into data science, and I've been doing it ever since, and I really enjoy it. So I've been with many companies, and throughout that I've come across optimization problems in a wide range of industries and different scenarios. And I am currently working for Advancing Analytics. We're a nice bunch, so if you want to come and speak to us, please do. So, what is optimization? Optimization, it's sometimes used as a bit of a buzzword in business to mean make better, but it's actually more than that in a lot of ways. So from a technical standpoint, it goes through like a mathematical framework. So you would describe it as convergence towards a global maximum or minimum through a set of actions or steps within a defined system. But a sort of nicer, more layman's sort of definition is the art of choosing the perfect set of actions to reach the ultimate value that can be achieved. And the way I like to look at it is, imagine you are racing, and you know somewhere out there, there is the perfect way of racing. So it might be the way you take the corner, the perfect speed, the perfect amount of braking. It might even depend a lot on that particular day, like the weather maybe, what kind of car you have, but there's the perfect steps that you could take to get the shortest lap time or total time around the route. And that's basically what it's about, the art of trying to find the perfect set of actions to reach the ultimate value. And it's not always achievable, and quite often you can't quite get there, but a lot of it's about using that logic to search for it. So why would you do optimization? So a lot of the time, if people think that they know what's going to happen through a lot of data science projects, they might think, well, I can do this myself. But quite often, problems are quite complicated, and often too complicated for a human to squeeze best performance out. So imagine a graph, like you have a 2D graph. A human can visualize that. Go 3 ways, yes. But if you start going up 4 and 5 dimensions of routes, it gets quite difficult for a human to visualize, and that's where a computer can help. And also, people don't think numerically. They see a tree in the distance. They don't say, oh, that's 35 meters away. They say, oh, it's fairly close, it's far away, etc., etc. It's also quite time-consuming, a lot of these steps when you can have the machine do it. So if you're building rotors and stuff, imagine if you had a load of staff and you were trying to optimize timesheets. This could take a long time, and this is where an algorithm might help you. Right, so now I'm going to start running through some use cases to give ideas of where you might want to apply it. So routing's quite an obvious one, and I'm sure a lot of you have heard about it before. There's plenty of software to do it. So let's just run through an example. So imagine this is London, of course, and you can see there in the bottom right, that's where the XL is. Now imagine if you wanted to come out this talk, go to all those points of your friends, and you needed to tell them about this conference, but you wanted to get back for a talk within 2 hours. And you had to drive, and you wanted to take the quickest route and make sure you're back. Now, if you ran it through an optimization problem, then you would get something like this. And you're back within just under 2 hours, which is good, of course. Now, you might think, I could probably just do that in my head. But one thing to bear in mind, or two things, is people don't know road distance, so they just look at that in terms of straight lines. And this is one of the examples where it's not always intuitive. So you see here, it sort of loops around a bit and does a loop rather than goes straight from one point to another. That might not always be obvious to the human eye. So it's very good for these sort of problems. This is, of course, a very basic idea. Normally in a business, you wouldn't deal with something like this. It would be more like this example. So let's say you're a company, you have a load of products that you're trying to sell, and you have to get them to these destinations. It could be toys, bread, whatever you're selling. And these are the sources here in red. And you have a load of stores to get to, and you have to travel by the road via these vehicles. Now, and you have a total of those to deliver. Now, everyone is probably aware how fuel prices are escalating at the moment and getting very expensive. So what you'd want to do is minimize the amount of road distance or mileage for the vehicles. And if you were to run that through an optimization problem, you'd get something like this. So this route minimizes the road distance, and it outputs from those sources that amount, and it makes sure everything's delivered without actually taking too much distance on the road. So it's really useful in that way. And of course, humans, they might give it a good go, but it's not always obvious. Marketing. So this isn't an obvious one. You normally think of marketing, and marketing is quite subjective. You think it's based on material, whether it's good or bad, you don't know, but the responses can be numerical. So in that way, you can actually monitor the responses, and then you can apply optimization. This is also a good example where if you use data science to do some calculations and work out sort of responses, maybe you do classification, it's going that bit further to actually decide what to do with that beyond that. So you're doing some marketing. Say you're looking at doing some television adverts, and you want to allocate spend to these regions, and they all cost different prices. So let's say, for example, in the Northeast, you can spend up to £100,000, and that will get you 100,000 views. And it varies in price. So in London, of course, London's expensive. £700,000 will get you 100,000 views. But that's also the limit. You can't really spend any more than that. the company wouldn't allow you to. And you also have to have, your company wants a minimum spend in each region of £1,000. And you've done your data science work and you've worked out that 100,000 views gets you different sort of responses in different regions. So in the Northeast, you might get 500 or so. So now you know roughly, of course it's an approximation, but what sort of responses you'll get. Now you want to decide how to spend your money and to get the most amount of responses. And you have a budget of £1 million. Not only that, you've done some more data science work, and someone's come around to you and said, well, we want to get some responses, but we've also done a bit of analysis to find out that actually there's another product that we're offering, and these particular regions are very responsive to this second product. So they might sign up for the first product, and then they might say, well, actually, I'd like to get involved with another product. So they want these weightings in these regions as well to make sure that you get that engagement. So taking this all into account, an optimization problem would look like this. So that would be, based on this, the maximum output you could get. Now, again, a person could probably do this, but I'd like to illustrate what the worst case scenario could be if you were really bad. So it's 800 fewer responses, you spent a lot of money, it could make or break. You'd imagine a person would get in between, but this is where optimization can really help within a business. All right, cooling systems. So there's been a lot of work on this. In fact, DeepMind managed to reduce the energy costs of one of the Google data centers by 40% using an AI model to do this. So they cost a lot of energy, and energy prices are forever increasing. So it's a very good use case for this sort of work. And I am not going to pretend I've done anything like what they've done, but this is just an example of how it might work if you were to do it yourself. So let's imagine you have a data center, and it has a maximum minimum temperature that can operate 80 degrees to -20. Beyond that, it explodes. And the temperature, the intrinsic temperature, is built up of the atmospheric temperature, the transfer rate of data, and the number of users. So it's a combination of those which create the intrinsic temperature within the system. You could do, again, data science work to work out the linear correlation between those three that will give you the intrinsic temperature. So that could be one reading. And then the energy is related to the change in temperature. For the sake of this demo, there's no coefficients there or anything, but the energy transfer is related to the change in temperature. So that's what you're looking at. So there's two scenarios I want to run by you. So the first one is just a basic cooling system without any sort of AI or optimization. This is just very basic. So it has a window. Ooh, running out of time. OK, so the other one is using AI to predict this. So it can have a set of actions. So it can increase by 3, it can increase by 1.5, not do anything, drop the temperature by 1.5 and 3 as well. Here's a quick illustration of what it will look like. So you can see here with AI and with no AI, the energy that it takes starts to rack up after a while, and this is where it can really help to bring down those costs. And here it manages to reduce it by 70%. Of course, this is a very naive model. The real thing would be more complicated than that. Some very other quick scenarios where you can use it in. You can use it in systems that rely on maintenance. Any system that has signals that you want to maintain and optimize, you can do it there. Scheduling, complex schedules. We've done that recently in AA. And you can also, quoting tool is an interesting one. So I've been involved with this as well, where you've had quoting tool where you have to give the cheapest cost for a customer, and there's something like 16 degrees of freedom, and you need to do it there. And yeah, and going back to the example before, anywhere where you can allocate spend, there's normally room for optimization. So, problems with optimization. Not every problem can be solved without stating the obvious. It's not a black box, and for example, you're never going to replace CEO with algorithm. Not yet, anyway. It's also, you have to make quite a lot of assumptions and approximations with a lot of things there, and you have to bear that in mind for when you're applying this to a real-world problem. Finally, this is meant to be bad problem, but it's good for me. It's not as automated, so there's not really any sort of off-the-shelf black box solution to this. It requires someone that knows what they're doing to sort of do the technical build and make sure it works properly. And if I've got enough time, I'll gloss over very quickly about the techniques. So linear optimization is probably the simplest method you can use. Quite a lot of nonlinear problems can be approximated this way. You can go to large degrees of freedom. It's a very good technique. And in those use cases in red, that's where I've applied it before. There's also something called simulated annealing, which could be used for routing, which I can talk about at the end of this if people are interested. Nonlinear optimization is a bit more difficult, and I've done problems with it. We're going up to like 16 degrees of freedom, and it can be quite difficult. And sometimes you have very non-smooth objective functions you need to solve, and it takes quite a bit of logic to work around. And then the real machine learning one is reinforcement learning, which is a great technique. It's the sort of thing that you can use for self-driving cars, etc. It's good in terms of it can handle unstructured data and things, so you don't need to define the system in the same way you do. It can handle non-deterministic scenarios. The problem with it is it's very difficult. It takes a lot of training, a lot of time to train the models, but it can be done. Right. So, yeah, I hope that gave some ideas or food for thought. It's something that people shouldn't forget about, and it's definitely worth exploring once you do that initial data science work to maybe think about maybe I could push this further with a bit of optimization. Cheers.